Well, all right then, 23rd or so, June, Thursday evening. Well, I thought I'd continue reading from the Fourier series book that's been so great. So far, it's established, first of all, some of the formalizations and the questions of formalism for rigor, mathematical rigor, that go into the definition of the Fourier analysis. Here's is called kind of the Fourier-style analysis, that go into the notions of what make for the convergence of these infinite series of these sums of sine and cosine functions by these coefficients that end up that for any bounded region for a classical function or a function under certain conditions, as it's drawn as in a chart from left to right without lifting the pencil and without going leftward after rightward or something like that, that what it makes it so is that you can make it possible that it's about how to define that function that can be described as polynomial or any kind of function, any kind of real function, can also be written in this way where, according to these integrals and forms about it, after something like a Rolle's theorem and some of these things that have to do where the differential is defined by the intermediate value or the midpoint theorem, the mean value theorem, and then from some of the properties of the sine and cosine, that they're orthogonal functions, so that their integral of their product is 0, or that their product times its weighting factor is equal to 1 in a given region, that it ends up making what was being called this windowing and boxing. Windowing as in from left to right, making it so for a particularly small region within this bounded area that's under analysis, and then boxing, figuring also how that from top to bottom it kind of fits in this space. That in this way, the Fourier-style analysis was formalized and made so that it could be well understood, and that if you have other systems describing these same kind of conditions that go into the derivation, then what could result was that a Fourier-style analysis, Fourier-style, can make for any other system where it can be possible to replace something like sine and cosine with other kinds of orthogonal functions that also have some properties that make them amenable or tractable to Rolle's theorem or the mean value theorem, which also are so about the linearization, small angle approximation, or the theta equals sine theta, and when x goes to 0 and this kind of thing. These are the only few properties necessary to get into then how then the convergence and the existence of the limits of the things make it so that they add back up, that then it's possible to write the series this way. And also a lot of times, because the higher order of these coefficients end up being in to the left or right of it in a way to make it possible to crunch and generate incrementally closer and closer values to this to compute the area under this function. This way, giving a means to make something after it's sensible, and then fungible also to get it to be tractable. That tractability is our goal after fungibility, after sensibility. Sensibility is that it makes sense for something. Fungibility is that piece by piece it can be pieced together, and then tractability means that there's available a method for it that kind of makes it tractable, like a tract, or toolable. I can read it, I can write it, I can tool it. These are the kinds of things that go into what make this a good thing. So then the author got into the notion of the surrounds of 19th century analysis, and why that was so important for real analysis is that a lot of what we end up having as formal rigor is, and today in the standard, is courtesy, the efforts and the communications, and what results for making the opinions being shared and commonplace and known among all the people who ended up being involved, that they agreed that it was fairly rigorous. And then in this manner, it could be said to have some mathematical validity, and that in the sense of being established, proved that it comes into a lot of the different things about real analysis. So who were discussed were people like, after Euler and then Gauss, then it got into Dirichlet, and Riemann, and the notion of Riemann's integration, and then into Lebesgue, Henri Lebesgue's measure theory. And then what's measure theory? Well, it's just kind of like when they say, well, what's a metric? It's like a meter stick. It means there's a way to say there's 1.0 everywhere, measure 1.0. That measure is pretty much the same way. It's like a meter stick that you can chop up into bits, and when you add it back up, it equals 1.0, measure theory. And so that's what, and then the process is, and then in this analysis, it was after showing what's going on, how it's windowed and boxed up with the Dirichlet kernel in the Fourier-style analysis, because Fourier had kind of invented this and made some of the initial geometric things which build the Fourier-style analysis. And then Dirichlet came in later and showed how kind of the formalisms kept it all together from, prove that this converges. Vis-a-vis, it mostly converges, it adds up. I used algebra and it wasn't wrong, this kind of stuff, into that it's closed. That then the idea of, after Dirichlet, then there's also discussion of Fehr. And then there was talk about, after Riemann, and then the piecewise continuity, from the left and right, say, when you split this region in regions, and it can have jumps, removable discontinuities or jumps that still kind of add up and in. The idea is then that this conditions make for, again, a midpoint type thing, that f of x from the left and f of x from the right, their average is what is established to be by the Fourier-style analysis in the middle. So with that said, then where we left off was reading about Lebesgue's measure theory, and the definition of integration. So let's see what we had here. And then it got back into the heat form, the heat equation. So the reading was up into the heat equation, existence of a solution, returned to the heated bar. So there's a wire or a bar, and the idea is there's a candle on one end, and how long does it take it to get uniformly hot throughout the entire thing? And at each point in time, and each point in length, what is the value? So there was talk about the assumptions go into the conductance and the capacitance, the constants that define this model, and then also a lot of talk about, well, what if it's more fluid and turbid or vorticial? What does it mean if there's like a heat wave or blob magmas that result, that there's like other models of heat that make it for whether it's really just attenuative and dissipative, or if it's also always got this non-zero part that's restitutive and oscillative, or it might be zero. It's always got a formal part that's either one of these that are rest in motion, or bouncing set, or something like that end up just being variables, symbols. If, for example, they're not real variables, they're always zero, but symbols for variables in what make for then what would be the higher order, super classical, nonlinear. That these are the things that go into the things. So here's the dog ear, the bookmark. Oh, here's this latest one. So we got up reading about into some of the exercises and into some of these sums of that look like these coefficients that are generated. It's an infinite sum of coefficient times e, this natural logarithm constant, and here it'll really have to be addressed some more the complex analysis and Euler's identity. E to the I pi minus 1 equals 0, or vice versa. The idea is that is, after this complex analysis book, that would be basically the next thing to read from about that. And that's basically what I went to, is reading in the complex analysis for the past couple of days. That's about that. And then into the theory a bit, So what it is about the complex analysis that it was to be determined is then for the existence of the conditions for the exponential function when it's taken to these various negative powers, and how it lives in these coefficients and elements of the Fourier-style analysis, that it is about the complex branch of those things, and to figure out if there's possible and how it's possible to make it for so that it's framed in things like this identity dimension and this identity dimension complex diagram as the envelopes of the things, what would otherwise be the singularities of things. Finding new things is kind of the goal and the role, because the idea is to find the new things that make it so that there's a certain fame in that. It's famous to find good, sensible, fungible, attractable things in mathematics, because someday it might save somebody a lot of time. So this coefficients was then as e to the negative n squared. So n goes from 1 to infinity, and so e to the negative n squared gets small, because a number, of course, to a negative number is 1 over that number to that power. And for a number that's greater than 1, 1 over that number is less than 1. And these are all positive numbers. Then if you take that to higher and higher powers, it goes to 0. Vis-a-vis, for, of course, for any number greater than 1, its higher powers diverge and go to infinity. It's said that it converges to 0, but it diverges to infinity. And so the behavior when two formulas both go to 0 is kind of well understood, and a lot of times it's said that their ratio is 1. But it varies. And because it's division by 0, it's an indeterminate form. And so then there are various conditions like L'Hopital's rule. L'Hopital's rule about you take the derivatives. If those also are the same, then maybe it's a ratio, and not just an indeterminate form. But here, though, when it goes to 0, then it cancels out the equation, equals 0. And in the case that is small, and these numbers there's an infinite sum of them, each one is pretty small, and they get smaller as the index goes out of the sum. So that's how they can have a limit and converge and not just go to infinity themselves. Anyways, any function that has a limit in this one of these infinite series, if they're all positive, the terms will decrease. Maybe not strictly monotonically, but over a large enough region, they will decrease. And in fact, then beyond that, they will decrease again and decrease again. Kind of delta epsilonics with capital delta epsilonics. Here they've been calling it big M, large number, and that M is greater than N and greater than N. And then there's that, with that in place, that's not quite sufficient to establish and guarantee convergence to a limit, that the limit exists, and that there's some point where it's that the least upper bound is so, but then there's these other convergence tests that make that so. And again, the most familiar infinite series is the negative powers of 2, 1/2 plus 1/4 plus 1/8 ... equals 1. And the other, and my favorite one is just the infinitesimals that sum to 1. It's like 0, 1 iota, 2 iota, ... infinity iota equals 1. But it's a special function. So e to the negative n squared pi squared, this is the ratio that sits in as courtesy Euler's identity. And then kt over a squared. Now these are parameters that represent a ratio of the properties of the quantities that affect the physical condition. K is this constant. T is time. This is the only variable, is the time. And a squared is the distance. Okay. And then times sine n pi over a. Again, it's in this ratio n pi over a. About the periods, and that the n is the index of the term, and sine n pi over a times x, so that then the sum of this expression is one part in time and one part in x, which is distance down the wire or the bar. At x equals 0 is where the candle is, and at x equals a is the length of the piece. This series converges to a function u from d bar. So d bar is this setup over d is description of the bar that the sets d equals x over t and r squared. 0 is less than x less than a, and t is greater than 0. And d bar is just inclusive. 0 is less than or equal to a and greater than or equal to 0. And t greater than or equal to 0. So it's got those endpoints in there too. So d bar to r, that is of class C2, it's continuously differentiable at least twice. In D is continuous on the set d naught equals xt and d bar t greater than 0. So it's just then excluding that one point there where t equals 0. And satisfies the boundary value problem set up in 1 through 5. And this was that in the two parts in a partials, time and x, that u sub t equals k u sub xx. So the first partial derivative with respect to of this function u in time equals k and times this partial differential, this u with respect to x taken twice. So the acceleration, as it were, in a sense, just taking dx dt, or here just du and dx, and this other one. Now that is setting those to 0 is then how it's solved. And then otherwise, as long as they're equals, isn't the way to do it. So there's various ways to consider for these implicits and what comes into it. And that's kind of what we're looking for, is these other solutions that live in the same kind of space, besides what show up as these solutions, with regards to that, then what would be these harmonics, and the whole idea of this harmonic theory adds up a lot of what would be these higher order solutions as soon as you get oscillation involved. Here it's just it's just warming up. In view of the preceding propositions, remains only to prove 5. Fix a point x in 0, a, which f is continuous, and define a sub n equals c sub n sine n pi array x, and g sub n t equals e to the negative n squared pi squared kt over a squared. That whole quantity. Then sigma, or the sum, n equals 1 to infinity, is a convergent Fourier series. G of n plus 1 of t is less than equal to g sub n plus t for each n and all t in 0 to infinity, and absolute value of g sub n t is less than equal to 1 for all t in 0 to infinity. Hence, by the corollary of theorem 8.3, the series 6 converges uniformly with respect to t on the interval 0, infinity, and its sum is continuous by theorem 8.4. Then u of x comma t goes to u of x comma 0 as t goes to 0, and because of 4, 0x comma t goes to f of x as t goes to 0 QED. Quod erat theorem strandum proof done. The end, of that section of the proof. Here again, recall that these are the conditions that are given why it converges, and according to a corollary that has some other conditions about why otherwise that not all functions that just diminish have a limit. Some do not. Some go to infinity. And it's given some examples. For example, a bar of steel, 10 centimeters long, has an initial temperature distribution given by Fx equals x. The ends of the bar are maintained at 0 degrees Celsius with the value of K equals 0.128 centimeters squared per second. That's the units of it. See? And A equals 10. 6 is a solution of this problem if the C sub n are computed using 7. And then you just plug in these numbers for K and T and A, and then you get this something like C sub n equals 2 over 10, integral from 0 to 10, x sine n pi over 10, x dx equals 20 over n pi times the quantity negative 1 to the n plus 1 power. And then that gives the nth coefficient in the series. And it's convenient because it's only got terms in sine, besides that the Fourier-style analysis has terms in sine and cosine, but in this case they're just one. Because of the exponentials, most of the terms in this series are negligible for t large enough. In fact, if we define alpha equals e to the negative 0.00128 pi squared is approximately equal to 0.987, there's u of x comma t is approximately equal to 20 over pi, which is approximately 3.14, times the quantity alpha t sine n pi over 10x minus 1/2 alpha to the 4t sine pi over 5x plus 1/3 alpha 9t sine 3 pi over 10x for t large enough. This is represented in figure 3.1 for t equals 10, 30, 60, and 120 seconds. Now, if you looking at these diagrams, you can kind of see what happens is they have a mean and it kind of grows over that, and then it kind of slumps off after it goes out. That's pretty much just kind of a wave as it crosses and accumulates and falls back to it. And then the idea is that if those were conditions where it was a really wobbly material, where oscillation came into effect, and for example, these sine and cosine had to come back together, and they ended up with both these terms, and they kind of had to add up when it was positive and negative, and came together oscillating this way. Then what would happen was that these forms you might still expect to show up in the middle of that, and as it establishes where it is, until it settles down, that it's the same kind of thing. It's usually called, when you talk about a distribution, and distribution in numbers is kind of like this. It has it's defined by any formula that has area under it 1. So a probability distribution is, when you say distribution, it almost always means a probability distribution, meaning for the values in its support space or its domain, that the values in the range are probabilities between 0 and 1, and the area under that for a continuous distribution is always equal to 1. So what you can happen is, like, if you flip any number of fair coins and you establish a value between 0 and 1, you can kind of look across that and pick a value for that, and that's as fair as saying it's as random according to that distribution. That things that are more likely have more weight, they have a higher value, and things that are less likely have less weight, they have a lower value. And then that the PDF is that the integral equals 1, and the CDF, it actually just ranges from 0 to 1. So it's similarly there as if you just say, if I could pick a value between 0 and 1 and stop right there, then that CDF is the same, is a function, find that for the same distribution. It's basically the integral of that as it goes to left to right. Then there's also the moment generating function, and I need to know more about that. But it does have to do about these, the exponents. The exponent, and especially the natural logarithm, which is discovered by Navier, excuse me, not Navier. Navier-Stokes is familiar and famous for something else in fluid flows. But Napier was this guy, and he discovered the natural logarithm, and also other things to do with logarithms. And while, and I have to confirm that, because while the Euler constant is the constant of the natural logarithm, the base or the radix of the natural logarithm, it was discovered by somebody else, and I'm not quite sure actually if that's Napier. Napier made the first logarithmic tables, and the tables were very successful because you didn't need to have a calculator because there were none. And with these tables, though, you could look up a value for a given power or log, and it would have somebody already computed it. And then you can use that to compute sums and products in the space of logs or logarithms, because it has an addition formula, so you can add them to compute their product, them as multiplying them. So of course that's the fundamental operation of the slide rule. Also, the slide rule is the meter, and then one of the meter is a linear scale, and the other one is log scale. And in this manner, you can line them up, and then whether there's 1 or 2 or 3 sticks, and then whether there's 1 or 2 markers on the slide rule, with lining up the pieces, and then checking the value, and then sliding the piece over, and then checking its value, and then with maybe a little paper arithmetic on the side. That the operation of the slide rule is a pretty cool thing. I have had a slide rule before. I have a slide rule. The calculator I have that I use most often is probably a pocket solar powered calculator that I got in high school, and it's on loan kind of, and it's got the scientific functions, what we call them, like sine and cosine and exponent and log and this kind of stuff. It's not programmable in a sense, but it does have maybe up to 8 place memory, and both clear entry and clear. And so in this manner, one can build up stuff in terms of properties of the usual applications. It's not a reverse Polish notation or that the other kind of hand calculator. the Hewlett-Packard mostly. This is just regular Texas Instruments or Sharp or Casio non-graphing solar-powered calculator that I used with some great success when a long time ago when I crunched all these numbers with it. And then I do have also like a reverse Polish calculator too. I only have 4 or 5 calculators, but they're mostly just museum pieces. The biggest computer I ever wrote a program for was at the university in the biology lab. There was this setup for running numbers on genetic data. And so what you do is you get a gene sequencing, and that might be a billion or 10 to the ninth something, 10 to the eighth, 10 to the 9 long in the human genome. And what you do is you run some algorithms on it to look for subsequences that match. And so anyways, this computer was what they call a rack system, which is like and then the computers in these days are basically organized in terms of what they call pizza boxes, or size 1 unit to 4 units. And so it's like 1 unit deep is about a couple inches high, and then it's like as big as a pizza box, a large pizza, and then 2 and 3 and 4 are like that big, and so that's traditional size of rack mounts in these racks in the rooms, where these rooms live in a world where they have a bunch of wires in and out, the cabling, and then they have a giant air conditioner, or else it would overheat because there's a lot of waste heat in these systems. So anyways, in this rack mount system, there's 2 of these racks, and there was 96 of these 1U, 2 CPU. They were Apple computers, remarkably, and then they were all put together with Ethernet. They weren't set up with like what's called InfiniBand, or otherwise they're networking locally, but they were like a NUMA architecture, something like that, which is if they were going to share a really large memory or core or something like that. So anyways, then what that had on that was either Silicon Grid Engine or message passing system. And what that is a way to find when you want to write a program and run it parallel on all these computers at once, which it's kind of like different than MapReduce, which is a way to really just scale out linearly and horizontally scale out algorithms that don't have too much in the middle, MapReduce. But what MPS allows is defining instructions to go out to all these computers, and then they all go fetch a piece of the file or whatever, and then they crunch away on it. So anyways, thus the question that now we face is, does the Fourier series of a continuous function that also has one-sided derivatives converge uniformly? Clearly, this question could not have been answered in 1829, when Dirichlet first proved the convergence of Fourier series, as the concept of uniform convergence had not yet been discovered. As it is, the same question was posed by Henrik Edward Heine, professor at the University of Halle. He was not concerned with any kind of heat problem, but rather with the following theoretical question. Now we've read this section before, so this is part of the historical section, but sometimes in picking up the pieces where there was left off, there's going back a little bit. So we'll get in like Heine, and not so much about Borel, but there's kind of the school of Heine and Borel that go into a lot of different things about the spaces and the combinatorics, because then, of course, this is also the very influential time of Georg Cantor, and he came in and made set theory. He was very much a proponent of that set theory became central in foundations of mathematics, and not least because he discovered or collected some theorems about uncountability. But it's very influential and central in 20th century modern mathematics. And so he's in the realm of these analysts who are much more. The reason why that's important was accepted because it was built in the framework of establishing results in these at the same time, so that they all kept up together. It's a little bit easier these days. All that's kind of cooled off quite a bit since then. So in trying to understand where things are and sit in that, it's gained a bit too much what you call the paper mountain or whatever. That these days, that's kind of canon. And well, there are lots of different modern approaches in theory that when we will try to address things like that, then they'll get to like category theory or whatever, type theory, mostly category theory, because the physicists come down from category theory and say, I don't care, as long I need to make it, and so they do it the way they want. And they say, now that's the foundations, but really it's have to address the same logical paradoxes, lack thereof. And of course that's subject for a different talk, but I enjoy talking about it because I have a few levers in there. Heine was at this time far from the Weierstraussian world at Berlin, but he was a student of Weierstrass and may have learned about uniform convergence before leaving Berlin, or may have heard about it from a new arrival from Berlin, Georg Ferdinand Louis Philippe Cantor, who had become a Privatdozent in 1869 at Halle. Before that, he taught at a girls' school, taught mathematics. Whatever the case, Heine knew about uniform convergence and about Weierstrass's proof that a uniformly convergent series of integrable functions can be integrated term by term. He also knew from Fourier's work, as we have shown in 2.2, that if the equation above holds and if the series on the right can be integrated term by term, then the coefficients are uniquely determined and have the values given by definition 2.1. Heine made the connection between these ideas and stated that if a function f of negative pi to pi, that interval onto r, is a sum of a uniformly convergent trigonometric series of the form given above, Fourier series, then its coefficients are uniquely determined and happen to be the Fourier coefficients of f on negative pi pi. It was in this manner that Heine posed himself the question, when does the Fourier series of a function converge uniformly? He provided the answer in a paper of 1870, a particular case of which, sufficient for our purposes, is stated below in Theorem 3.2. Then let's talk about Heine, and then they went to work with Borel, and then about Schoenflies. And Schoenflies does kind of like when we're talking about symmetries, submersions, and sheaves. Schoenflies is famous for the crystal classes are lattices, and the symmetries exhibited by objects that fit together, objects of a uniform shape that are polyhedral that fit together, like crystals, and the, like face-centered cubic is a kind of crystal that the cube is the most familiar such structure to anybody, with its 6 faces squares. Now, he identified a bunch of different things to do with the symmetries involved with these. And so then when they're having these kinds of mechanics and the situations of the mechanics, they go into such notions of rigid lattices and deformable lattices. That this is all basically a reflection on lattice theory. And the rigid and the deformable, and what happens when you shake it, or it gets crushed or deformed. And what happens in these is that it's established for any kind of resonances or vibrations or oscillations that occur in these systems. There as about this thing in these symmetries, that those establish the bounds and establish the middles and establish what vibrations and resonances would naturally carry out and fall down. And so this is, I wish I remembered the guy's name from this other reading the other day about the guy and what he did was he studied drumheads. And he'd put sand on a drumhead, and then he'd hit the drumhead at various points on it. And the sand naturally goes into patterns. And so he studied these, and I'll recall this at a later point and bring it back up, because it becomes kind of a thing, because it really represents what is a fundamental action that arrives at then just this natural spacing of occurs. Because basically it's just like the direction he was hitting the drum and tapping it in that spot, it showed that the impulse out of his arm caused that a point was reflected into the center of that drum head, and that's where the things started to line up. For example, if he spun around and hit the same spot from a different angle, it would be at a different spot, indicating how the entire action that is only small in his action over time and in the system of resonances adds up and makes for, out of this nonlinear, again, the linear. So that's that's kind of what to figure out for these kinds of things, to end up having a pretty good mathematics for these things. So looking forward here, Fourier series converges. Having exhibited, and then we already kind of read this, the maximum principle. So we got in this maximum principle for the heat equation, and this is where we got in the discussion of the delta epsilonics for the large, and this windowing and boxing, and then this arbitrarily large number, which it really is only effect when it goes to infinity, but there's just kind of made a conceit. It's like it's arbitrarily large. It's arbitrarily large. Yeah, that ends up making there's still a pathological case where it's arbitrarily large, but at the same point in time, it's what they call it here, this maximum principle. Weierstrass proved in his lectures at Berlin that a continuous function on a closed and bounded set has a maximum value and a minimum value on that set. The boundary value problem at theorem 3.3 is well posed in the sense of Hadamard. Now I need to understand what is the sense of Hadamard, because there was some mention of Hadamard in an earlier point in this book, and I'm not too familiar with the works of Hadamard. But what Hadamard is famous for is at least a couple things. And so one apparently is the posing of boundary value problems, and that they're well posed. And then another one is the computation of the value of n factorial. The factorial function of an integer is that it times each number less than it. 10 times 9 times 8 times 7 times ... It's a large number. Kind of like, 1, 2 times 3 is 6, times 4 is 24, times 5 is 120, times 6 is 6 times 120 is 720, and so on. That he computed a way to have a closed form for that. So for something like 1,000,000 factorial, he's got an equation, and it's close. It's an approximation. And similarly, Stirling is most famous for when you think about how to count how many combinations there are in a set or permutations. These are part of what are called combinatorics, how to combine things, and what are the counting arguments that result how to combine things. Now, in mentioning before the probability distributions for the continuous distributions, for the discrete distributions, the probabilities are defined by the counting arguments and the combinations and permutations for the classical probabilities. So, for example, if you have 2 dice and they're each from 1 through 6, then it adds up according to the counting arguments what you can expect, why that 7 is the expected value, because it has the most combinations that add up to it. Out of all the possible combinations, each one's given the same weight. Then it happens when the sums or numbers add up, that's why 2d6, which is usually the way to say 2 many dice of sides equals 6, a roll of them, that the classical probabilities are built from the counting arguments of combinatorics. So, in combinatorics, then there's a couple different functions, and one is you have n many elements, and you can choose k many. N choose k. It's called the choice function, n choose k. And so that if when that's large, then sometimes you deal with n choose k, and sometimes you deal with n minus k and choose n minus k. That those two products represent, like, well, here's all the ones that could be out this way, and here's what's left on the other side. These become these factors in the middle, the levers either way, that end up having these kinds of things. So that's one example function. So Stirling invented also what are called the cycle numbers and the subset numbers. So that's like for n and k, the set of size n, and for k many, how many cycles there are of this length, cycle numbers, and how many subsets there are of this length, subset numbers. So these also have various ways to compute them for closed forms. And so n choose k is most familiar after Pascal or something like that, and then gets into all the arguments that build up about that. Why that becomes in classical probabilities is called counting methods or counting arguments, all the things that add up for that kind of stuff. And so Stirling invented these, defined these numbers, invented some forms of them. And Stirling also computed an approximation for n factorial. Now I found an approximation for n factorial, but the one I wrote is in the factorial and the exponential. It's in the exponential. It's kind of surprised to find, but it's pretty close. It's pretty close. By that the order of the error term, I haven't analyzed its error term yet and its asymptotics to establish that it has a vanishing error as it gets very large. But it's different than Hadamard's, and it's different than Stirling's, and I haven't seen it before otherwise. And anyways, it's an example of a closed form. I'll detail that some more later. It's about that factorial exponential identity in square Cantor space that I discovered about 2003. So, anyways, when it said that Hadamard well-posed boundary value problems is to be established what exactly that means, because there may be cases where A, there are conditions where they're not well-posed, or B, there are other conditions that establish well-posed boundary value problems beyond those of Hadamard. Otherwise, they would just say it was well-posed. But here it's that they've kind of put that brick above Hadamard's head, and so as long as he doesn't have to get out of the way of it, then nobody will know the better. It's a principle after the maximum principle. All right. Note that this theorem goes beyond stating that the problem is well posed and asserts that the solution is non-negative. In fact, if we assume, as we shall from now on for convenience, that temperatures are measured from absolute zero, then f must be a non-negative function and u must be shown to be non-negative. So here there's this other idea is that the oscillation would have at some point negative. If it would be like going back and forth, that would be wise. So at the same time, it's a totally nonsensical value to assume ever that it changed, and it was, and it assumed a negative value. So then here in this context, as we've been discussing it, or as I've been discussing it, and you may have possibly seen a bit of, is this the identity dimension? Everything is positive numbers to begin with, and so when there's subtractions, they still just live inside these positive numbers. So that would be for building up these kinds of cases where it sort of arises that these kinds of conditions will still be real. If instead a different scale of temperature were used, then both F and U should not be smaller than a certain constant. Negative 40 Celsius is the same as negative 40 Fahrenheit. For instance, this constant is negative 273.15 if the temperature is measured in degrees Celsius to kelvins. So Celsius in centigrade is that centigrade is 0 to 100 to the boiling point of water that at sea level. And that's about the thermal first law, where the definition of calorie is calorie boils or increases by 1 degree to boil cubic centimeter of water. Kelvin, and his absolute zero, has the other definition of calorie. And so the first definition of calorie lives, and then there's the third definition of food calories, which are not involved in this at all. So the first definition of the thermodynamics first law, calorie, is about boiling water and a teaspoon at a time. And the second law, thermodynamics, is about going to absolute zero, attenuation and dissipation. So they're kind of framed, one's in terms of 1, the other one's in terms of 0. And then in physics, what they have everywhere is basically thermal second law, and it's named for Kelvin, and this concept of absolute zero. And that at that point in time, then the energy of the vibration of objects, that is how they represent how much heat energy they have within them, 0. And so that's just kind of to indicate then, would Fourier's equations for heat be good all the way down to 0 and all the way up to an arbitrarily large number? Mostly. But this is for a perfect conductor of heat, and it varies. Here, Fourier's analysis is about this piece of metal, and it has certain properties that make it more like so, where it wouldn't necessarily be so. Is any metal at absolute zero a superconductor? I think so, yeah. To conclude this section, we discuss the asymptotic behavior of the solution. It is expected on purely physical grounds that if heat is allowed to escape at the endpoints of the bar, and if their temperatures are kept at 0 degrees, then the temperature at every point of the bar will naturally decay from Fx to 0 as time passes. Mathematically, this is strongly suggested by, and you can replace 0 with whatever is the ambient or surrounding temperature, that the sufficiently large body has a sufficiently neutral temperature that doesn't change. It's background temperature, according to background heat, that there's no surplus there, that all the heat can escape from the bar, and it wouldn't boil the ocean of the surrounding thing. Mathematically, this is strongly suggested by the decaying exponentials. And can be proved as follows. If m is such that absolute value of c sub n is less than m for all n, and if we define alpha equals pi squared k over a squared, which is kind of like pi times root k over a, all that quantity squared. And r equals e to the negative alpha t. Now, this isn't the complex value, as we've been discussing in terms of the complex analysis. I want to understand Euler's identity. But it is between 0 and 1. We obtain the following bound for the nth term, absolute value of c sub n e to the negative n squared alpha t times sine n pi over a x is less than or equal to a capital M, big M, in infinity. But here it's just a bound. It's established that this when this is the arbitrarily large bound, that this other expression is less than it. E to the negative n squared alpha t is less than or equal to big M. E to the negative n alpha t equals mr to the n. Because they were given expressions in terms of r and alpha. And so it's established the absolute value of this comes in under this inequality, that its magnitude is bounded, that it lives under this otherwise. So then you can say it's kind of windowed and boxed, finite. Then since 0 is less than r less than 1 for t greater than 0, and since the sum of the geometric series, which is a power series for these numbers that are between 0 and 1, since the sum of n equals 1 to infinity of r to the n with absolute value of r less than 1 is r over the quantity 1 minus r. like the right. In the geometric series, that's kind of when there's talk before about that levers and kind of like n minus k and k and n minus k. Then here this r and 1 minus r and their ratio about them is a similar kind of thing. The idea is to figure out how to take advantage of the arithmetic, and that 1 is the multiplicative identity and 0 is the additive identity. And 1 is here's also the maximum, or it's the bound for these numbers. And then 0 is also the multiplicative annihilator. Anything times 0 is 0. Anything times 1 is anything. It's the identity or the annihilator, respectively. So the idea then for the singularity theory that's been being discussed in the multiplicity theory is to look at the geometric series this way and the expressions that go in the derivation to making it so. How it's possible to look at how to make it so that then there's, for things like the geometric mean, the arithmetic mean, and the harmonic mean, what ends up being a valuable, it can be evaluated in terms of how then it's derived in terms of these parts of the arithmetic, and then how it can be levered in, and I'll look to define that word a bit more in a minute, into a can opener of sorts, for then figuring out how to figure out what happens when certain very contrived scaffolding on either side can arrive that is balanced and makes for more sensibility, fungibility, and tractability in looking for results in the outside, what focus in the middle. So since that is r over 1 minus r, we have that the absolute value of u, the function of x and t, is less than or equal to this big M over e to the negative alpha t over 1 minus e to the alpha t. E to the negative alpha t, excuse me. This shows that u sub x sub t goes to 0 as t goes to infinity. Moreover, the quotient u of x sub comma t goes over e to the negative alpha t remains bounded as r goes to infinity. In Hadamard is well posed with the maximum principle as of Heine. Those being established parts of this derivation where if they don't hold, then it would take alternate conditions to make them so hold. Or if they don't hold, then there would have to something else to interplay to make it so that it still stays together. And so insofar as where something like this Fourier-style analysis is really well held up, or it's still got to affect the physical law no matter what are the inputs or outputs or the surrounds, then gets into these notions about where effectively those reflect variables in the derivations, in the theorems, and the part of this definitional and derivational dynamics of these derivations, which everybody uses. Everybody uses these exact same results in every course that covers this subject matter, including here. Non-zero temperature at the endpoints. Undoing boundary value problem. U sub t equals k u sub xx, so the first partial of u with respect to t equals k u, the second partial with respect to x. And if u u 0 comma t instead of being 0 as t1, and u of a comma t instead of being 0 as t2. So it starts as if with a ramp, or assuming whether t1 is greater than t2 or t1 is less than t2. Then as heat is applied, then you can imagine it's just going to average out. When we talk about this average out, then there's again this geometric average. It's like this r and 1 over r. The arithmetic average is the average, it's a sum over 2. And it's the middle value between the numbers. It's the mean, and vis-a-vis the arithmetic, geometric, and harmonic means. They're called means, not averages, but so the geometric mean, arithmetic mean, and the harmonic means each have these things that need to go into covering how they're derived and defined and devised to make for these levers. A lever is the simplest tool, one of the simplest tools. And here, via an application of force, according to the information chosen where to place the lever, then it can be made use a mechanical advantage of the lever, so that what it results is that it can basically linearly multiply the force that applied at a point at a cost of having a strong enough lever to hold up to the deformation that otherwise would occur. So if you've ever used an iron bar to lever something, you know that it's like the guy who said, just give me a place to stand and a lever that's strong enough and a fulcrum that's well supported enough and I can move anything, as long as the lever is long enough to give me enough mechanical advantage and I can pick it up. That here also that the force of the lever can very readily bend an iron bar or steel bar or something like that. That's exactly how rebar is bent. It's just about long enough to be just about strong enough that just about a guy throwing out his back can bend it using the rebar bender or this kind of stuff. It's designed in those terms. It's like, why are flour sacks a given weight? Because that's exactly the weight that the flour sack guy can carry. So anyways, these levers here, though, the idea is that they're mathematical. Part of the mathematical scaffolding is you can imagine any kind of contrivance, any kind of arbitrarily contrived, made up, fabricated thing you can imagine of any number of components, like a lever, and apply any number of things to this thing to help it along. It's like, well, we had to figure out this water coming down the board, and it was flowing, and we want to make it faster, so we use it as a squeegee. You can imagine that as anything to do with any kind of external input is a lever. It's a lever. So, and so the second boundary value problem is like the first one, but it's just already has initial values at the beginning and end. T1 and T2 are non-negative constants, and f is a continuous non-negative function with a piecewise continuous derivative, and such that f0 equals t sub 1 and fa equals t sub 2. F of 0, the function at 0, and the function at a equals t the first and t the second. The new endpoint conditions are not linear, since the sum of solutions that satisfy 11 and 12 do not satisfy 11 and 12. Oh, so that otherwise the linear superposition principle of these differential equations, this is kind of remarkable, because I thought this would fall out kind of a different way. But what the author's describing is, because I was thinking maybe in the integral curves way, or I don't know, but then the author is describing it in this differential curves way, and it's establishing that, it's not linear because no longer do those functions add up for that. So they're going to transform it, I imagine, to a case where they do, by making a change of variables. Oh, here he comes. If you denotes the temporal distribution, then from the first of the equations, we get this, and then he makes up a function in terms of, kind of like before, it was just n pi and a and k for t, and then x. These ratios that have already gone in to make those linear equations, There's just another one here too, so that's pretty cool. Well, all right, that's what we're getting into reading so far today, about the most usual application of solving differential equations, transforming them to linear equations, and solving those. There's a book on number theory, and this integers, the theory of integers. They're moduli. Integral moduli is any multiples. The sigma is for the sum and over the index and the variable. So sum of each of the terms by their value. Capital Pi is for product, multiply the terms. So products. So the author has these things. Let's review this book for a second. Chapter 1, Preliminary Considerations, Introduction, Summation, and Multiplication Notation, Postulates for the Positive Integers, Mathematical Induction, the Well-Ordering Principle, Equivalence of the Principles of Induction and Well-Ordering, the Division Algorithm, Positional Notation. So largely here in this discussion of arithmetic so far, this number theory is arithmetic, and arithmetic is number theory. So here in these talks, of course, there's been a lot of talk about the deconstructive account of arithmetic and having addition on one side and division on another side and having them fit together in the middle. Having a continuum even first, that the integers arrive for arithmetic from properties of geometry, the space existing. That's kind of how that's been discussed here. But such formalities and formalism fit very, very neatly and well into the standard modern mathematics formalism in the 20th century and today. There's not a replacement for it. All right, yeah, imagine we'll talk about this more later. I enjoyed reading this to you today, and I hope things are well wherever you are, and that things are nice, or that you're making things better, as imagine you may be. And so have a great day, and until some such other time, so long.